Cryptography. It's pretty much the invisible shield that protects everything we do online, from our banking to our DMs to just about everything else. But how does it really work? Well, today we're going to pull back the curtain on the incredible math that turns total chaos into rock-solid security. Let's get into it.
So, we've all seen that little padlock icon in our browser a million times. It's basically the universal sign for, hey, you're safe here. But what's actually going on? What's the magic happening behind the scenes that takes the wild public internet and turns it into a private, secure tunnel just for your information? That's exactly what we're going to unpack.
All right, here's our game plan. We're going to start with why we even need this stuff, the digital privacy problem. Then we'll look at the fundamental tools cryptographers have in their belt. After that, we'll tackle the biggest challenge of all, how to share secrets safely. And finally, we'll see how it all comes together in a massive system of trust that you use every single day.
So why do we need all of this complicated math in the first place? Well, the thing is, our data isn't just in one place. It's kind of everywhere. It exists in different states, and each of those states is a potential weak spot, vulnerable in its own way.
Just think about it for a second. You've got data at rest, that stuff just sitting on your hard drive or on a server somewhere. Then there's data in transit, which is anything zipping across a network, like an email you just sent. And finally, you have data in use, which is info that's actively being crunched by your computer's memory. Securing all three of these is the fundamental challenge that cryptography was built to solve.
So, to solve this three-part problem, cryptographers have come up with a really powerful toolkit. These are the core building blocks, the fundamental principles they use to create encryption that's actually secure. Let's take a look at the most important ones.
The first tool is a concept called confusion. The whole goal here is to make the link between the secret key and the scrambled-up text as messy and complicated as humanly possible. Seriously, it's like taking a recipe, but instead of just swapping ingredients, you throw the actual instructions into a blender. No one's going to figure out how you made that cake.
Next up, we've got diffusion, and this creates something called an avalanche effect. It's so cool. It means if you change just one single letter in your original message, it triggers this massive, unpredictable cascade of changes in the final encrypted text. And that's absolutely crucial because it stops attackers from just fiddling with the message a little bit to try and guess what's inside.
And finally, there's hashing. Now this is a totally different kind of tool. Its job isn't to hide data. Its purpose is to create a totally unique, fixed-length fingerprint for a piece of data. You can feed anything into a hash function, a password, a whole movie, whatever, and it spits out this unique string of characters. And the key thing is, it's a one-way street. You can't ever go backwards.
And please, remember this distinction. Hashing is all about integrity, not secrecy. That digital fingerprint analogy is perfect. You use it to check if a file has been tampered with, because even changing one comma will give you a completely different fingerprint. But you can't use the fingerprint to reconstruct the person, right? Same idea. Okay, so we've got these tools, but this brings us right to the central, age-old problem of all cryptography. If you and I want to have a secret chat, how in the world do we agree on a secret key to use without someone listening in on that conversation too?
This is where we run into two different ways of doing things. You've got symmetric encryption, which uses one single key that both people share. It's incredibly fast, perfect for encrypting tons of data, but, it's got that key sharing problem. Then there's asymmetric encryption. It cleverly solves the problem with two keys, a public one you can shout from the rooftops and a private one you guard with your life. It's brilliant for sharing secrets, but it is so much slower. So what do?
The solution is actually pretty genius. You just use both. We start with the slow but super secure asymmetric method for one and only one critical job, to safely agree on a temporary one-time use symmetric key. We call that a session key. Once both sides have that key, they switch over to the fast symmetric method for the rest of the chat. It is literally the best of both worlds.
But this just raises another question, doesn't it? When a website sends you its public key, how do you know it's really them? How can you possibly trust a server on the other side of the world that you've never met? Well, for that, the internet has a massive global system called the Public Key Infrastructure, or PKI. Honestly, just think of it like a worldwide passport office.
And this system has a few main players. First, there's the digital certificate itself. That's the passport, right? It officially ties an identity, like a website name, to a public key. The certificate authority, or CA, is like the government agency that issues the passports. And the registration authority, they're the ones who do the background check to make sure you are who you say you are before the CA ever issues that passport. This whole system is held together by something called a digital signature. It's how a certificate authority stamps a certificate to prove it's legit. What they do is they take a hash of the certificate, a fingerprint, and then they encrypt that fingerprint with their own private key. Anyone in the world can then use the CA's public key to unlock it, which proves it came from them and that the passport hasn't been faked. It's proof of who sent it, that it wasn't changed, and they can't deny they sent it.
So what your browser does is actually follow what's called a chain of trust. When it gets a website certificate, it doesn't just take its word for it. It looks at who signed it. Then it goes and finds that authority certificate and checks who signed that one. It keeps following the chain up and up and up until it hits a root CA, one of the big, super trusted authorities whose certificates were already installed in your browser from the get-go.
And by the way, not all these certificates are made equal. The most basic kind, a domain validation certificate, just proves that someone controls the domain name. It's the bare minimum to get that padlock. But an extended validation certificate, that means there's been a much deeper investigation into the actual legal organization behind the website. That's why banks and other high-security sites used to get that special green bar in the address bar. It's a sign of a much higher level of trust. Okay, we've got all the pieces on the board, we have the toolkit, we know how to exchange keys, and we have a system of trust. Now, let's put it all together and see what happens in that tiny fraction of a second when you connect to a secure website. This is the SSL/TLS handshake. The whole thing happens in a flash. First, your browser says hello to the server. The server sends back its certificate. Your browser checks that certificate all the way up the chain of trust. Then, they negotiate the exact rules, the specific encryption they're going to use. After that, your browser creates a brand new, one-time use session key, encrypts it using the server's public key, and sends it over. From that moment on, everything is locked down tight with that fast, secret session key.
And that negotiation step is all about agreeing on something called a cipher suite. Just think of it like a recipe for the secure connection. It spells out exactly which algorithms they're going to use for each part of the process. One for sharing the key, another for scrambling all the data, and a third for making sure nothing gets tampered with along the way.
And when we talk about how strong this encryption is, you'll hear numbers like 256-bit. What that means is there are 2 to the power of 256 possible combinations for the key. That's a number with 78 digits. I mean, to put that into perspective, trying to guess that key would be like trying to find one single specific atom somewhere in the entire known universe. It's not going to happen.
And here's the most mind-blowing part. This entire complex dance, the request, the certificate check, the negotiation, the key exchange, all of it is over and done in milliseconds. It happens before you even see the web page start to load. It's just a stunning piece of engineering. So really, that's the big takeaway here. This intricate ballet of mathematics is happening all around you every single day, protecting your information. It's what takes the absolute chaos of the open internet and turns it into a secure, private channel for you. That little padlock represents a gigantic global system of trust and some of the most powerful math ever put into practice.
But of course, technology never ever stands still. The very foundation of all this security relies on math problems that are just too difficult for our current computers to solve. But what happens with the rise of quantum computing, which could potentially shatter these algorithms one day? Well, the race is already on to build a next generation of cryptography. What's that going to look like? That is the next great challenge. Thanks for tuning in.